of Electrical Engineering at IIT Gandhinagar. He has done his BTech degree from University of Kerala and MTech degree from Department of Electronics and Communication Engineering, NIT Rourkela, and PhD degree from School of Electrical Sciences, IIT Bhubaneswar. He is one of the renowned faculty member of IIT Gandhinagar, and he has received more than 2800 citation with H-index 30 and I-10 index 73. His paper on advances in active noise control has received more than 200 citations, and he has been applying the optimization techniques over the years to various applications of electrical engineering. So, welcome Dr. Nitin to this faculty development program on advanced optimization technique with MATLAB. So, over to you.
Okay, yeah, thank you, and good evening. Yeah, so our topic is nonlinear system identification and optimization approach. That is our topic. So before we go into optimization, we will have to understand what is system, what is nonlinear in that system, and what is identification. So what I have done is, I have tried to take an example of a problem where an identification of a system is necessary or it is indirectly used. Okay, so that will give us a clarity on how things are going to work. Okay, is it audible?
Yes, it is perfectly audible.
Yeah. Can somebody from the audience put in chat that it's audible? Yes. So when the second time I asked, is it audible now? I actually did not make any sound. Okay. So you can think that it's not hearing because the network is bad, or because your ear is bad, or because I am not speaking. Understood? So we have two different scenarios here. So the problem which we are looking at first here is, do you have a hearing loss? Are you able to actually hear or not? This is not the question about whether in the WebEx you are able to hear or not, or in the YouTube you are able to hear or not. In the real world, is your ear working or not? That is the question I am asking. So if you have doubt whether your ear is working or not, what we do is that we go to an audiologist. Audiologist will do a hearing test, and then they will plot a graph. So let me plot that graph for you. So that graph typically will have frequency on the x-axis and some hearing level on the y-axis, and it will be dependent on frequency, and it will say some graph like this. So the meaning is, if this is 250, 500, so 1K, something like that, 8K, something like that, or 4K. It's typically up to 8K maximum they plot. I think 4K they plot. So what is the meaning of it? If I have a 500 hertz signal played in front of me, I will only hear that sound if the magnitude of that sound is above this point in terms of the level. So this is level 1. So I will only hear that sound. Which sound? This 500 hertz component of that sound I will only hear if if the sound is played at a level L1 or above, at an amplitude L1 or above, then only I will be able to hear. So that is understood. So this is a very much frequency dependent thing. So for example, around 1.2K, I will be able to hear that sound even if the sound is above L2. So it is not like your glass. Okay, if you go to a shop and buy a glass and say, I need minus 2.5, minus 1.5, plus 1.2, nothing like that, because there is a dependency on frequency also. You may be hearing well in some frequency, may not be hearing well in some other frequency. You can hear 500 hertz at maybe some amplitude level, to hear at 2 kilohertz, you may need a lesser amplitude level or a higher amplitude level. So it is again person dependent. Suppose I have a hearing loss in the sense, suppose I went for uh, a hearing test, and then I found that my hearing profile looks like this, suppose. So now the meaning is, the blue one is for the second person, red one is for some normal people, and blue one is for somebody else. What is this graph giving me is that, for example, for 500 hertz, if I am playing a sound at level L1, that will not be audible to me. Only if I play at level L3 or above, this sound will become audible to me. So I can say I have a hearing loss for 500 hertz. But for example, if you see this frequency, maybe 200 hertz, I am able to hear at L2. Normal people are able to hear at L1. So hearing loss doesn't mean that you are going to have a loss across all the frequencies. You may have loss in some frequencies, you may not have loss in some other frequencies. Understood? This is the meaning of it. So I can say that this the blue curves person is having a hearing loss, because this person cannot hear sounds which are normally heard by people at 500 hertz, 1 kilohertz, in that type of range. But for 4K and 3K, this person's sensitivity is higher. Okay. So what is the solution to the problem? The solution to the problem is not to ask the other person who is speaking to you to speak louder. That is not a solution to the problem. The solution to the problem is what is called a hearing aid or an assistive listening device. Or a hearing aid. Okay. What it in the crudest form, if you want to imagine what it does is it takes an input signal uh, from a microphone. You put a mic, take the input signal, pass it through some box, and play it through a loudspeaker, and you do some sort of an amplification. But this amplification is a frequency dependent amplification, because your loss is in the 500 hertz type of range or 1K type of range. You do not have a loss in the 2K range. So you do not need an amplification in the 2K range. So what we do is that 5K you amplify, 2K you don't amplify. So it's like a filter or something like a frequency dependent amplification can be introduced over here, and you can consider this as the crudest form of a hearing aid. Understood? Okay, this is the problem. Now let's come to our problem. So suppose I have a hearing loss. How the hearing aid will look like is, where is the mic of the hearing aid and where is the loudspeaker of the hearing aid? Okay. So typically, if you see some people who are wearing a hearing aid, you might see something like a clip which is put on the backside of an ear. There is some hardware which is on behind the ear, and there is some connection which is going to inside of the ear. This is how it typically looks like. So what happens is the mic is somewhat over here or behind the ear. So that is the microphones which are there, and the loudspeaker is very close to the ear, just inside or somewhere slightly outside. Okay, that's how it is being done. Now what happens is, because I have hearing loss, what I have done is I have amplified the sound, because it is not like a normal hello. This hello has been amplified and it is played through the loudspeaker. But where is the loudspeaker? The loudspeaker is very close to the microphone. So what happens is, in addition to the amplified hello signal which is going into the eardrum of the person, this hello will be also picked up by the microphone. Understood? So what I am saying is, so there is this mic, I will put a different color. So there is this mic, this is passing through some system is amplifying it, it is playing it through the loudspeaker. Okay, this is what is happening. But now the sound goes to the eardrum. I am okay, I am able to hear it. But the sound will also go back to the microphone. The sound can also go back to the microphone. Why? Because the speaker and the microphone are very close to each other. Okay. This is what is called acoustic feedback. This is called acoustic feedback. where you have a loudspeaker and a mic which are close to each other. The amplified sound which is from the loudspeaker is fed back by the microphone, and what the microphone will again do, give it to the DSP system. System will again amplify it. Again it will get played through the loudspeaker, and a loop is getting created. Understand? So this is what we typically see if you are in an auditorium or somewhere, you are listening to a talk, and suddenly you hear this whistling sound. Some beep some type sound is coming, correct? So what they typically do, is that they go and reduce the gain. They reduce the gain, that is one. Or you move away from the so how it happens is, you are speaking on a mic and there is this loudspeaker somewhere over here, and you move to the mic to near the loudspeaker. So this feedback loop is created and the sound is getting amplified, and you are getting this beep type of sound, or the amplifier is getting saturated. Okay. So what I will typically do is I will run away from that region, and I will speak at some other position, or I will ask the person to reduce the amplification, reduce the gain, and then my feedback problem and this beep sound will go away and I am able to continue. But both of this cannot be done in our problem statement, because can I reduce the gain? No, I cannot reduce the gain because I already have a hearing loss. I am not able to hear the sound, correct? Because I am not able to hear the sound, I have put this device. And now you are telling me that you reduce the gain. That is not possible. Second is, can I separate the mic and the loudspeaker? Can I keep the mic somewhere else and loudspeaker somewhere else? Okay. Why I am keeping it near to the ear is to mainly handle what is called directionality. So there is one more thing called directionality. Directionality in the sense, when somebody is calling you hello, you also want to know from where this person is calling, correct? You want to know whether this person is going from your right side or left side or back or front. So I need to identify the direction of the sound. So how we are able to identify the direction of the sound is because you have two ears, first of all. Second of all, you have a head in between which is opaque, correct? You have a head in between both the ears which is separating the two ears. Okay. So your brain is able to identify that some signal is coming at some time, and after some delay that signal is coming to another ear if somebody is calling from my this side and the opposite from the other side. So I am able to understand that somebody is calling from here or calling from here. But suppose I had put the mics on my eye position, what would have happened? Both the both the signals would have been similar, and I will not be able to identify from which direction the sound is coming. So it is my purpose that two ears are there and both ears are not in the front near our eye position, it's over here. Fine. So if I want to use the pinna, use this direction and use the head to say that direction is also important, I don't want to move my mic away from the ear. I want to keep the mic near the ear only. Okay. In a normal scenario. That is why the two solutions which we get in a auditorium example, you cannot use in this example, because you cannot reduce the gain and you cannot separate the mic and the loudspeaker. These two problems cannot be solved. So I will need a more intelligent solution to this problem rather than the other two crude solutions which are there. So can I have a signal processing solution to the problem? That is the first question. So the question is, I have uh, a signal which is, this is the mic. So the output of the mic is the speech plus feedback. Okay, so the output of the mic is speech plus feedback. And my objective is that the feedback should be removed from the signal so that my user is listening to only the actual speech which the person wants to listen. Okay. So I have one microphone. One microphone is giving me two signals. Those signals are speech plus some feedback signal. And I want to remove the feedback signal from the speech plus the feedback signal to get only the speech signal. That is our objective. Can I put a filter over here and get this output? Can I put a filter over here and get this output and remove the feedback is the first question. It is not a trivial problem, because if I want to separate the signal and noise in a normal scenario, what we do? We look at the Fourier transform and then see whether my signal and noise are separated in some domain. Correct? Separated in maybe in the frequency domain. But here, the feedback is also created from my own speech. My speech is amplified and fed back. Understood? So these are mostly in the same or similar spectral regions. So a simple filter is not a solution to the problem. A simple filter is not a solution to the problem. So this problem is again not a simple DSP solution. Understood? So what we do is what is called an acoustic feedback cancellation. So what we do is we are going to do something called a feedback cancellation in hearing aid. Okay. So this path over here, let's see the path. There is a speech which is coming. Speech is picked up by the microphone. That signal, let's assume that nothing else is there. It goes to the forward path. Forward path is the amplifier. Okay. Or the amplifier which has been curated for your hearing loss. Understood? So every person who is wearing a hearing aid will have a different filter or a different amplifier or a different algorithm, which is not algorithm, different what you can say characteristics of the filter which is going to be used in the forward path, because that has been created for your hearing loss, not for somebody else's hearing loss. And then it is played by the loudspeaker. This is our normal scenario. And then what happens is this, that signal which is going through the loudspeaker is again picked up by the microphone to produce acoustic feedback. So now my question is, I have a signal xf of n. I have a signal xf of n which is equal to, let's assume that speech is x of n, even though I should not be write it like that, x of n plus f of n. Okay. So this is not a very accurate representation. Understood? Because that sound is not in the discrete time domain. Okay. This is, I have written x of n, f of n. These are all discrete time, discrete signals. Okay. But for simplicity, I am writing it like this, saying that my mic is picking a signal which is x of n plus f of n. F of n is the feedback which is going to be coming from there. So x of n is the signal. Can I subtract from here an approximation of f of n so that the overall signal will become an approximation of x of n? This is the problem statement. Understood? So the mic signal which is measured by me is x of n plus f of n. Now I am saying, can I somehow generate an approximation of f of n such that f of n is getting removed from that x of n signal, so that the net output of the summation or the subtraction is an approximation of the speech signal. That is our object. So what I am trying to say is, suppose I know, suppose, that is our first assumption, suppose I know what is the equation which represents this blue path. Understood? What is the equation? Means, can I write a mathematical expression for this line which I have drawn from A to B? Can I write a mathematical expression? Can I write what is the relationship between the signal at A and signal at B? Understood? But signal at A is going through a loudspeaker, which is a physical system, and then it is passing through the air, and then it is picked up by the microphone, and then it is coming to B. So can I replace, or can I find an equivalent, what you can say, or an expression, or a filter equivalent, or a digital equivalent, or a, what you can say, mathematical expression for this path from A to B? If suppose I can do that, that will be called a model. And this path from A to B, I will call a system. Understood? So this physical path, the physical path from A to the loudspeaker to the air in between to microphone to B, this entire thing I will call it the system. And if I can have a digital equivalent of that, understood, like a filter or something like, or a mathematical expression which is representing that, then I will call that a model. Suppose I am able to create that model, and this box over here is that model. This box over here is that model. Suppose it is that model. Then what happens? Y of n is passing through A and passing through the physical system and reaching B to form f of n. You see here, what I am talking about is this y of n signal is passing through A and it goes like this and goes like this to produce this f of n signal. If that same y of n is passed through this lower path through this, I will be able to create an approximation of f of n if the model of the feedback path, this the physical path, is a good one. Means if the upper path has been modeled effectively by the lower path, then theoretically I will be able to have what, a cancellation of f of n and f cap of n, and I will be able to reduce the acoustic feedback. So this person who is using the hearing aid or this device will be able to use at a higher amplitude level, but even listen properly and without any feedback, because whatever feedback is going to be created, whatever feedback is going to come is going to be cancelled by this internal system of feedback cancellation. This is not that trivial because I said in the simplest form. Okay, this is not that trivial because of multiple reasons. First is this path is not fixed, because the moment I move my ear, move my head, my path has changed. I am getting a mobile phone call. I keep the phone near my ear. My path has changed. Understood? So all of those situations are going to come. So this path keeps on changing. So this feedback cancellation system should immediately identify a new model. Understood? So wherever the system is there, whenever the system is changing, a new model has to be identified in real time. Understood? Then only this cancellation is going to work. Okay, understood. So what I am saying is, this is an indirect application of system identification. It is actually a feedback cancellation problem, but indirectly what I am trying to do, I have a physical path from A to B. That A to B path is replaced by a digital equivalent, which is called the feedback canceller over here, which is a filter. Okay, which is a filter. Okay, fine. One thing I forgot to tell in the previous slide is, why should the sound escape the ear? Means you can very well close the ear with an ear plug or something like that. Understood? So then the feedback will be less. So what happens is, if I try to close your ear, because this device is not an entertainment device. This is a device which is going to be worn by this person for 24 hours every day. So if you try to close your ear with your finger and say hello, what happens? What happens is that you are getting a different hello. You are not feeling the your normal hello, because there is a bone conduction sound which is also going into the ear. Okay. So this is called occlusion effect. So if I am going to create this product, I should be able to also give the user the best possible experience, the most realistic experience I want to give to the user. So I want to keep my ear open. So I want to do open ear devices, so that this is worn continuously, ear is open. This occlusion effect, that effect is called occlusion effect. When you are able to close the ear and then you try to speak, that weird type of sound which is coming is the occlusion effect. So I want to avoid that also. So I would keep that. So that is why it becomes more important that your solution is not a, what I can say, physical barrier solution. Physical barrier is not the solution to this feedback problem. It has to be an electronic solution. Okay, it has to be an electronic solution or a digital implementation of an algorithm on top of the device. Okay. Now let's look at the modeling problem, because that is what is our topic right now, is that we are going to do system identification, and we are going to do nonlinear system identification, and then we are going to say it can be done using an evolutionary algorithm. So these are the three levels which are going to be there. So I think you have understood why we need a model. Okay, fine. Fine. Now I will give you another example, because in this figure I have written that modeling of an acoustic path is what I am going to do. Acoustic path means any what I can say, air path between any 2 points I can consider as an acoustic path. Okay. So for example, now you are listening to this talk, what you can say, in a small room, using a speaker. You are listening to this in an auditorium. I am telling the same content. Your ear is also the same, but you hear actually different hellos. Correct? If I say hello, you hear different hellos. Why? Because the sound which is produced into the room is getting distorted or is getting affected by your room before it reaches you. That means the room has a characteristic which is modifying the sound before it reaches you. Understood? So that characteristic is can be, what you can say, represented as something called a room impulse response, or an RIR. Understood? So your small room will have one RIR, your another room will have another RIR. Every seat in a means all those type of different impulse responses. Every seat in an auditorium may also have a different impulse response from the speaker to that position. Understood? So if I want to characterize that particular room or a particular acoustic path, I am doing a modeling operation. Let me tell you what is the modeling operation. So you see here. So I have a speaker, I have a mic. So I have a loudspeaker here and I have a mic here, and sound is passing from here to here. You should not draw this wave like this because it is a longitudinal wave, but for simplicity I have drawn it like this. Okay. So I have a loudspeaker and I have a mic. Then I am generating some signal X of n. I am generating some random signal X of n. This signal X of n is passed through the loudspeaker. So this signal, random signal X of n, is generated by me, and this generated signal is amplified, passed through a DAC, and played through a loudspeaker. What the speaker will do? The speaker will move, the diaphragm will move, the sound will get produced, the sound will travel through the air, it will reach the mic, and the mic will pick up the sound, and you are going to get this signal DFI. So I am going to get this signal DFI. Okay. So this entire thing is our system, if you remember the previous example. Okay. If you remember the previous example of our hearing aid, this entire acoustic feedback path is similar to this path. Understand? So that's why I have put this dotted box around here and calling it the system. Now my objective is I want to create a digital equivalent of that system, which is called the model. And that model can be a simple FIR filter. Okay, simple FIR filter in the sense I can have some delay over here and some multiplier over here, some adder over here, delay. This can be your model. Model can be a simple FIR filter. Model can be a neural network. Model can be a spline filter. Understood? So many different types of models can be used. If my system is linear, I could easily go for an FIR filter. FIR filter is good enough because that's a very simple model, simple type of model which I can take. But if my system is non-linear, and if I try to model that system using an FIR filter, that may not be a very effective modeling, because I am trying to what? I am trying to create an equivalent of a nonlinear system using a linear system. That can only be an approximation. Understood? But if I am able to use a nonlinear model to model a nonlinear system, that would be a very effective solution. Then that is called a nonlinear system identification. Understood? So you have a system, you are identifying it. You are identifying it by creating this model. This model can be linear or nonlinear depending on whether the system is linear or nonlinear. Okay. So if my system is linear, I only need a linear simple model. But if my system is nonlinear, a linear model is not a good solution. I may need a nonlinear model to be used. This is the idea of nonlinear system identification. But how will I know whether my system is nonlinear or not? Understood. Under what condition is my system nonlinear? Okay. So suppose I take this example of FAR filter and apply a 100 hertz sine wave as input to the system. What is this filter doing? It is multiplying 100 hertz by some value. So for example, these multipliers are 2, 3, 2, suppose. So it is, what is this system doing? This is, let it be x of n minus 1, x of n minus 2, y of n is equal to 2 into x of n plus 3 into x of n minus 1 plus 2 into x of n minus 2. This is what the system is doing. So I have a multiplication operation, I have a delay operation, I have an addition operation. So if I give a 100 hertz signal to this filter, what is this filter doing? Multiplying by some value. If I multiply a 100 hertz signal by 2, will the frequency change? No, the frequency will still remain 100 hertz, only the amplitude has changed. Now if I have a 100 hertz signal and I delay by some unit of time, will the frequency change? No, the frequency is still the 100 hertz signal. If I add a 100 hertz signal with another 100 hertz signal, will it become some other signal? No, it will remain a 100 hertz signal. So what we are seeing is that this system is not creating any new frequencies. System is not creating any new frequencies. Whatever frequency is there in the input, only those frequencies are coming in the output. But it's not necessary that every frequency in the input should come at the output. But you cannot find any new frequencies at the output in this case, in this linear system. But suppose I put a block over here which is equal to square block. So I have an FAR filter, and at the output of that FAR filter I created this block called square no, nonlinearity. I have introduced some nonlinearity. So now what happens if I apply a sine theta as input? The output will become what? Sine square theta, which contains what? Cos 2 theta will be there. So if I apply a 100 hertz signal, that 100 hertz signal, the system output can be a 200 hertz signal because new frequencies can be created. So I can then say that that system is a non-linear system because I am having a system where new frequencies are being created by the system. And it is highly likely that new frequencies are created in the system which I have drawn here, because these loudspeakers are typically nonlinear. Typically square and cube nonlinearities are there in the system. And these are physical system, and depending on age also nonlinearity can change. Understood? So if I want a realistic implementation of this model, if I want a very realistic implementation of this model, it is not a good idea to do a modeling using a linear system. I should be trying a nonlinear system. Sorry. Understood. So this is what is. So now what happens is, so I first pass the x of n through the system and I got d of n. The same x of n I pass through my model. Model will give me some response y of n. And I have a difference between this d of n and y of n, which I call e of n, which is my error signal. Understood. Now if you see, this is similar to our what is our objective? Our objective is to make this model behave similar to the system. Understood? We want what? We want our model to behave similar to the system. So this is like a, what you can say, supervised learning situation where you have a teacher and a child, and we are trying to make the child behave like the teacher. Correct? Understood. So like any other neural network case, I could formulate an objective function and create this into an optimization problem. Correct? So I could say I want to do an E square of n minimization. I could say. Understood? Or I could say a summation of several E square of n minimization. Something like that. Or it need not be E square of n. Some function of V of n can be considered as an objective function. And we can now formulate this entire problem into an optimization problem. And that optimization problem could be now solved using a multi-agent optimization algorithm, which you have studied earlier. Understood. So in the current form, this need not be solved using a multi-agent optimization algorithm. Not necessary here, especially when the system is linear. It is not such a complicated problem, correct? But when it becomes nonlinear, there are multiple minima, etc., and then you may need an evolutionary algorithm or some other multi-agent optimization. So in a simple form, what we do is that we define the error signal E, which is D minus Y. But what is Y? Y is A transpose X. What is A transpose X? This signal over here is your X, and this is your A vector, which is A0, A1, etc. You multiply and add, you get this output, which is equal to Y of n. Understood? This is the thing. Fine. Now let us see. And it is not necessary that it has to be an FAR. It can be an IAR. It can be a neural network. It can be anything else. Okay. So suppose I am considering an IAR filter or an FAR filter. Now instead of taking an adaptive filtering methodology for doing the system identification, I could simply consider that this is an optimization problem where our objective is to minimize some function of E of n. Some function of E of n has to be minimized. So something has to be minimized. And what is the unknown to be estimated? The unknown to be estimated are these multiplier values, or the coefficients of the filters are what is to be estimated. So I have an n-dimensional unknown vector to be estimated, and I have an objective function given to me. So I could easily formulate this problem. I could easily formulate this problem as an optimization problem, as a multi-agent optimization problem, correct? For example, if I want to solve this system identification problem, suppose using a, what you can say, PSO or some other algorithm, okay? So this entire vector of unknowns, how many unknowns are there? There is L unknowns from the forward path, and I think M unknowns, sorry, L plus 1 unknowns in the forward path and M unknowns in the feedback path. So I have an L plus N plus 1 number of unknown. One vector is to be estimated. So I am doing a search in the L plus N, M plus 1 dimension space for that solution, which is going to give me the best possible value for a given objective function which I am defined over here. This is how we could formulate this problem as a what you can say, as an optimization problem which can be solved using a multi-agent optimization algorithm. Now you see here. So here I have taken cuckoo search, but you can take PSO or anything like that. So I could call it particle, sorry, I could call it particle 1, particle 2, P2, etc. Pn. So what I will do, I will pass a vector of some value, some input, a stream of input is given to the actual system. I get some response. The same stream of input is given to a model. Model is that FAR or IR filter, where the multiplier values are this P1 vector, that vector which is coming from PSO or Coco search or some other algorithm. You can consider that as similar to this filter over here, where A0, A1s have been randomly selected. Randomly selected means in the n-dimensional space, it is some point in that space. Okay. So what we do in a normal evolutionary algorithm, you do the initialization where all these particles are random. So P1 is random, P2 is random, Pn is also random, some random position vector. But when I give that input x through a filter where the multiplier values are p1, I am able to get an output y1. Similarly, through output p2, I am able to get an output y2, and similarly, I am able to get an output yn. So instead of having one system getting identified, I am actually seeing n different systems which are getting identified in parallel, with each system corresponding to one position vector. So each of the particle will now give me an error, e1, e2, etc. ens are there. Understood? Now I collectively do this optimization and try to keep on move the position similar to PSO or any other algorithm. I try to keep on moving the position. And finally, when it reaches an optimized point, what will happen typically? All the P1 to Pn will look similar or will be similar. Then I will stop my system identification. And whatever P optimal vector I got is equal to what? The coefficients, the multiplier values which are there in my model. So I have done a modeling process. Now this, when it comes to nonlinear models, there are multiple options of nonlinear models, standard options of nonlinear models. One is a Wiener model. Wiener model, what we typically do is that we have a linear system and a a linear model and a nonlinear model which are in cascade to each other. So I have a linear and then it's followed by a nonlinear, that is called a Wiener model. Okay. So for example, if I am having a, okay, now let me take the next example. Or I could do something called as a Hammerstein model. Hammerstein model means I have a nonlinearity followed by a linearity. For example, suppose I have a system which is a loudspeaker followed by this, like this, and now I am trying to create a model. This is how we did it earlier. But now if you see, I told earlier that this fellow is likely to be nonlinear. Likely to be nonlinear. This is most probably linear. So the entire system is a combination of linear and nonlinear, actually a cascade of nonlinear and linear, the system. So the model which I am going to select could also be a combination of nonlinear and linear. That could be a good match, where this n fellow will try to model the nonlinear part and L fellow will try to model the linear part. Understood? So I could, so the first decision I have to take for a nonlinear system identification is what type of model I should be using. So I have to decide whether I should be using a Wiener model, which is a linear block followed by a nonlinear block, or should I use a Hammerstein model where I have a nonlinear block first and a linear block second, or should I use a Hammerstein Wiener model? Hammerstein model, Wheeler model is a nonlinear block followed by a linear block followed by a nonlinear block. It's an NLN. So in some papers they write NLN model. So it's a Hammerstein Wiener model. So you take this decision on that. Second decision you have to take is what should be my N, what should be my L, and what should be my N. Understood? So because I have so many different choices available for N. N means what? A nonlinear model. A nonlinear model can be a neural network. Nonlinear model can be a spline filter. Nonlinear model can be anything else. A linear model can be an FAR filter, for example. Understood? Understood. So there are so many different options which are available. So first I decided based on the application which I am going to, based on my domain understanding of which system I am trying to model, I have to first decide, I normally first decide what type of model to use. Should I use a Wiener model? Should I use a Hammerstein model? Or should I use a Hammerstein Wiener model? That decision is to be taken. Second decision which is to be taken is what should go into the N and what should go into the L. Understood? That is the second decision which are to be taken, which is to be taken by us. Understood. So if I am doing a, suppose I decided that for my problem statement, it's a Hammerstein model, that means it is an n followed by L. So I will be having parameters of n to be updated and parameters of L to be updated, because it is equivalent to two separate models which are cascaded with each other. So this multi-agent algorithm should be searching for unknowns for n and unknowns for L together, with some optimization problem where the objective function is something like this. Okay, where an optimization problem is formed and we are trying to find the n. So what we will do is that we will quickly look at what some other possibilities of n, means what could be some simpler n models which can be used. So what I want to use is look at some what you can say nonlinear networks which are basically covered under this class of filters called linear in parameter nonlinear filters. Okay, linear in parameters nonlinear filters. So these are nonlinear filters, but in terms of the unknowns, this becomes linear. That makes the implementation much more simpler. And these are based on what is called Cover's theorem. Cover's theorem, it is there in standard our neural network books. It will talk about Cover's theorem. What it is saying is that a complex pattern classification problem cast in a high dimensional space non-linearly is more likely to be linearly separable than in a low dimensional space. So it says there is some low dimensional space, there is some high dimensional space, and you go from a low dimensional space to a high dimensional space non-linearly, and once you go to the higher dimensional space, your problem is more likely to be linearly separable. It is written linearly separable, much simpler, you can assume, than in a lower dimensional space. That is the idea of Cover's theorem. So all of these networks like functional link networks, spline filters, LIP filters, all of them typically use this idea. This idea is that you go from a low dimension to high dimension and then see that whether it becomes much more simpler or not. For example, if I think of a FLAN or a functional link network, what it does is that you have already seen these red points in the previous filter, and you already saw these multipliers in the previous filter. If this box in between, which is written as trigonometric expansion, was not there, it is the FAR filter only. But now we deliberately introduce this box in between, which is called a trigonometric expansion, where what we are doing is, see, what was our normal filter values? X of n minus 1 and x of n minus something. This is what these three things were there in the FAR filter, which we saw earlier. Now what I am doing is, so I have this x vector which is equal to x of n minus 1, etc. Now I create a new f vector which is equal to 1 x of n sine pi x of n cos pi x of n, etc. Okay. So what has happened is, if x vector, the first vector is of dimension 10, so my FAR filter would have had only 10 multipliers because I was in the 10 dimensional space. Now what happens is, after the expansion has happened, what has happened? This is of size 10, this is also of size 10, this is also of size 10. So you see a 10 dimensional problem has now become maybe 31. If I have suppose stop here, this is 1. So it became a 31 dimensional problem. So what I am saying is, this was a 10 dimensional vector. Now after expansion, it has become a 31 dimensional vector. And so After expansion, I only need to multiply by 31 weights and add together, and then also this problem is likely to be simpler, is our argument, is the argument of this filter. Okay, so and then what I need to find out? I need to find out this 31 unknown values. This can be done using a 31 dimensional search. In the sense, for a piezo in a 31 dimensional space, you are looking for a position, and the best value of that position vector, which will give me the solution to the problem, is the solution to the problem. Understood? So unlike an MLP or any multi-layer network, there is no backpropagation, there is nothing like this, because this is just a single layer network. Okay, and why it is working? Why do you think it is working? Means if you see, it is typically, if you see, this is like a Fourier transform or type of a situation, correct? So you have some sort of a function, and that function we are trying to approximate using sines and cosines. Understood? Of multiple different frequencies, multiple different amplitudes added together. Understood? So I am trying to use a sinusoidal basis function to try to do this entire make this neural network work. This is one idea. But I might be able to better approximate, have a better model if suppose I have a, because this sine waves amplitude can be made larger or smaller. That's all. That is the only control we have in flying. But suppose I have a exponentially decaying sine wave or an exponentially expanding sine wave, where you have also control on the way we decay the sine wave. Understood? So we have a change in the amplitude, change in the what you can say frequency which is there, and also there is a change in the way in which this decaying is going to be done. Then it becomes what is called an adaptive exponential finite. Okay, so where you are not using a sinusoidal basis function, you are using a decaying sinusoidal basis function, where the decay factor is also going to be updated in every, or is to be estimated in every iteration, so that you are going to have a very good approximation of this. So what happens is, this is how the expansion looks. So what is the change? The change is this box. This box, earlier I said I am just using a sine and cosine expansion. Now I am saying I am not using a sine and cosine expansion. I am using a different type of expansion based on our ideas from signal processing, saying that okay, this is a better way of approximation. So if you could use a decaying sinusoidal, that might be a better solution. Okay. So what happens is you get a different expanded vector. It is very simple only. You see, this is already there in the previous case. Now what we are having extra is that you have this term over here, e power minus x. This is already there in the regular plan. But this can make my what you can say model better, especially when systems are changing faster. Okay, when you have systems which are changing fast, this type of a nonlinear model could be a better solution. Okay, so now, so for example, so now if I give a full example of a Hammerstein model, I could have a flan and an IAR filter. It is an N and an L in cascade. So now I know that I have some parameters of the first block and some parameters of the second block to be estimated. And I use some evolutionary algorithm or some other algorithm to estimate it, just like what I discussed earlier. Understood? So this is how the final network will look like. So you need to estimate these parameters are unknown, these parameters are unknown, these parameters are unknown. Okay, so how many unknown parameters are there? R plus L plus P. So my search is in the R plus L plus P dimensional space. I am trying to search and trying to find the solution. Understood? So this is another filter which you can have a look, is called the spline filters. There are Wiener spline filters. Understood? Here you see this is a linear This is the nonlinear. That's why it's called a Wiener. Okay, earlier one was called Hammerstein because it was nonlinear first and linear second. Here, typically what we do is that we have an FIR filter, and then you have a block which is a spline block where it can go from linear to nonlinear depending on the system. So it can be a line, it can have a different shape. Everything is done through spline interpolation. Okay, so those are options which are available. Understood? So finally, when we are doing a nonlinear system identification, you see here we had a system which is a combination of nonlinearity and linearity. So you have some parameters to be estimated for the nonlinear block, some parameters to be estimated for the linear block. Together I have an unknown vector, and together I estimate the different errors which are caused by these different possibilities, and you do an optimization and then you find out the best possible value. Okay, so there are so many different algorithms which have come which can do this one. Okay, fine. I think what we will do is that we will discuss some things again in the tomorrow session at 4 o'clock. Okay, a little bit of thing which if something is remaining, yeah, otherwise if you have any doubt you can ask in chat. Otherwise we'll stop here.
Yeah, participants, you can put up your queries in the chat box. Nitinji, you can on-share the slide.
You can ask tomorrow also. Okay, so you can think about it, and then if any doubt is there, you can ask tomorrow. Okay.
And just wait for
Yeah.
another 1-2 minutes.
Yeah. Yeah. So the complexity will be definitely affected because in a linear system you have only n number of parameters. But by doing a nonlinear model, you are having significantly higher number of parameters. But by carefully choosing the n block, because you may not have much control on the L block. L block will be typically IR, FIR, those type of blocks. But by carefully selecting the n block, by selecting a low complexity n block, your overall number of parameters to be estimated will be significantly less compared to a different type. That's why we discussed this single layer low complexity network here, because so that the dimension of the problem will remain significantly lower compared to a different neural network or something else which we are going to use for the n block. So selection of n will be crucial in this case. Okay, that's how it is going to be affected. Okay. And these networks, this complex, it's not very complicated, complex because it is just an expansion and a multiplication. So it can be very easily done. In MATLAB Central, these codes are available. You can easily simulate it and see it's maybe a 10-line code. That's all. That's that simple. Yeah. Okay.
Okay, thank you.
Okay. Thank you. Okay. Bye.
Thank you. See you tomorrow.
See you tomorrow.
So participants, our next speaker for today, Dr. Rasna, is about to join. So please wait for a couple of minutes.
Hello.
Hello, Dr. Rachna.
Hello, sir.
Welcome.
Good morning. Good evening, sorry. One second. I'm just. I'm just quickly sharing my screen.
Yes, yes. Please share your screen.
Okay, here it is. I think it should be visible now.
Yes, your screen is visible.
Yes, fine, sir.
Yeah. So, participants, I welcome Dr. Rachna Gupta to this faculty development program on advanced optimization technique using MATLAB. Dr. Rachna Gupta has a vast experience in the AI industry. Prior to joining the industry, she has completed her PhD degree from our Electronics and Communication Engineering department at MNIT Jaipur. Presently, she is for last almost 5 years. She has been working in the various position in the industry, and she has a very uh, large experience on working on these multi and many objective optimization algorithms. So today she will be delivering about the many objective optimization algorithm GA3 and its application. So
So, allow me 2 minutes.
yeah, no problem, no problem at all.
Okay. Thank you, sir, for this wonderful introduction. So, here today, I'm going to start with the basic approach of, or I can say the algorithmic model, what we um, basically follow for the development of the NSGA3, which is again a modified version of the algorithm of NSGA2. So we are going to start our all the discussions. First, understand that why we moved over from NSGA3, from NSGA2 to NSGA3. Why that is the requirement came. Um, in NSGA2, we were solving the multi-objective optimization algorithm. We will understand some just a reminder that what exactly it was, and then we'll understand that what is there into the NSGA3, which is a many objective optimization algorithm, but in a multi-objective space, just to visualize that how these things are working. There are various steps. Basically, there are not multiple steps. There are only 2 3 steps, which is the normalization and association, for which we need to design some reference points. So we will discuss all this in detail, but in very briefly in this 1 hour. So first we understand that why we need this many objective optimization algorithm. So in multi-objective optimization, when you are dealing with 2 3 objectives, objective just to give you a brief idea, that objective means, for example, you book a ticket of train where as a user you want to purchase the ticket in such a way that the price of the ticket should be minimum, and as well as the time to reach from source to destination should be minimum. So this objective, this is nothing but a objective space. uh, the optimum solution is nothing to get that particular train number or train ticket, so that this both the objective can be satisfied. So this is a multi-objective problem where the objective is in the range of, or we can say, the less or equal to 3. When we go ahead of this, so this becomes a many objective problem. So now while solving the real world problem, there are the situation comes where we need the optimal solution. I'll tell you that when the such situation will come, but for now just understand that while solving the real time problem, we need to solve we need to get the optimal solution to satisfy our many objective requirement, whether it's a minimization, maximization, or it's a combination of both. Now, just to give a brief idea that what exactly we are doing in NSGA2, and where, like, almost I can say that the half of the processes what we do in NSGA2 we are